The Build Show Build Boston series is sponsored by Allura Fiber Cement Siding, Mitsubishi Electric Train US, Roseburg, Schuco USA, and Warmboard.
Hey, Build Show Build Boston. Steve Basic Architect here. You guessed it, it's wall framing day. Nothing more exciting to see this thing come alive in 3D. No intro today, let's get after it. All right, so we're talking about wall framing today. There's a lot of exciting stuff going on, guys, framing walls, standing them up around us, but I think it's really important before we get to some of the action that we actually understand what are the pieces that we're using, what are their names, what's some of the building science behind a wall assembly. So we're gonna run through a whole bunch of that, and then we'll get into the actual framing aspect and putting some walls together. So first off, let's talk about what we're using. So obviously with exterior walls, the common material is a 2x stud. Now, historically, we started out with 2x4s, we moved up to 2x6s in our climate zone, and it is somewhat dependent on climate zone. The rating, insulation rating and building science rating of your wall system is tied directly to the climate zone you're putting it in. So for example, in Florida or South Carolina, Georgia, we might not have to build as much of an insulating wall as we would build here or say in Minnesota or Montana for obvious reasons. So here, typically we build with 2x6. The spacing, just like floor joists, when we talked about it in floor framing, you have the option to do 16 or 24. 19.2 is probably an option. Can't say I've ever seen one framed. So basically 16 or 24 inches are your option. Here we're doing them 24 inches on center. And we're using two different kinds of studs. So the most common is just basically a solid stick. We call it a 2x6. The actual dimensions are 1.5 inches by 5.5 inches. The 2x6 comes from before it gets all dressed and cleaned up. It's basically the rough cut piece of wood. So 1.5 inches, 5.5 inches. They come in all the standard lengths. You can get them into 8s, 10 footers, 12 footers, 14 footers. But here we have a number of tall walls, and so we're actually moving to an LVL stud. So you can see this is made up just like plywood. Again, when I was out at the factory, these things get made up in 4 foot wide by 66 foot lengths. It's absolutely incredible. The tour I got out of the factory. And then after they get made up as these giant LVL slabs, then they simply get cut to the 5.5 inches. So you can see they're very much exactly the same dimension. The nice thing about this is you get a nice crisp edge. So the perception is that it's really clean framing as opposed to the little rounded edge there. But the reality is these are a lot stronger and they're a lot more stable. So we have a number of places where we have some tall walls where we're using these for the strength, but we're also using them because when you start getting to walls that are 14 feet tall, 15 feet tall, you're at the risk of twisting and warping and all of that. So in a way to avoid it, we go to the engineered stud. It just makes for a stronger, more stable wall. Now, in other areas where we need columns, we're actually using LVL, or basically engineered wood columns. These are nothing more than the stud, but you can see these are in 3.5 inch thickness, 5.5 inch. And these just take the place of, steel columns, lolly columns, built up stud work. Historically, we would do, 3, 4, 2x6 studs that we would gang together. But in lieu of that, we use a lot of engineered wood products. One, we know exactly what the load that these can take. So, and they're dimensionally cut, so they fit right inside of our wall system and able to pick up, beams along the way. As far as the header goes, and the header is nothing more than a beam that goes over the window. So we basically have our wall, and we want to cut a window in there, well, we have to introduce some kind of support above the window. So the LVL gets called into duty. The LVL is, again, just basically a sheet of plywood. It's just 1 3/4 inches thick. And in this case, they're 9.5 inches deep. We'll talk about those a little later. In terms of the wall sheathing, we're using a Huber Engineered Woods Zip R sheathing. You can see it says Zip R system, R sheathing on the outside. And what they mean by that is the standard zip is a 7/16 inch OSB, oriented strand board, which means it's made out of a series of strands that get intentionally laid in a specific orientation at the factory so that they can develop a strong sheathing panel in the 7/16. So you can also see on the outside, it has this green stuff on here, the green color. I mean, I'm sure as you drive around, you see a lot of green buildings going up. Zip is pretty much the go-to sheathing for most of the residential projects that are done across the country. But this one has a little bit of a twist. Because we're climate tuning it to our climate zone 5 here, we've actually added 1.5 inches of polyiso cyanurate here. And so they make the zip, they send it out, and then you get this piece of polyiso that gets adhered to it. Now, the 1.5 inches there provides an additional R9. So in this one sheathing, I get the weather-resistant barrier because it's integrated into the panel. I get the structural rigidity of the shear panel, and I get the insulating value of a Zip R9 all in the same material. Now, I know what some of you are saying is like, you said structural rigidity. Yes, even as a Zip R9, there is a shear resistance to this panel. Now, if I put the panel on top of the wall framing without the insulation, the shear values are going to be a little bit higher because the nail is placed in what's called single shear, meaning that the panel is directly attached to the wall framing. Because of the displacement of the 1.5 inches, it puts the nail in what's called double shear, makes it a little bit more complicated for the shear path to work in our favor. So you get a slight reduction when you use this, but it's still strong enough to meet all of the codes. And again, this whole house has been fully engineered and reviewed by our structural engineer. So that's the Zip R sheathing. But the Zip system, as it's called, doesn't just stop at the sheathing. They actually provide a tape, so that gets taped all of the joints, and that's their standard flashing tape. It's 3.5 inches wide. It gets placed on there, and they actually provide the Zip system roller, which you can see it has little Z's in here. So as you roll it, it embosses these little Z's onto the tape, so you get a really quick quality control just by visually inspecting it. And so the beauty of that is as they claim, the Zip R sheathing is not just an R sheathing, it is a system. So again, we get that weather-resistant barrier, we get the insulator, we get the shear panel, but the minute I attach that tape, we have a very effective air barrier. And I know this because I've done a number of houses where we've framed them and didn't cut the holes to the windows, where we just tested the Zip R sheathing. And we'd get numbers down in like a 0.3 ACH 50, air changes per hour at 50 pascals number. So it is an extremely effective air barrier if installed properly, and the tape gets installed and rolled and all of that good stuff. So anyways, we're going to move down the wall here. Let's talk about some of the components that make up a wall frame. All right, so we'll move down the wall here, and let's talk about some of the names or the nomenclature in a wall framing system, right? We talked about it a little earlier. I mentioned the word stud. So you can see we have our common studs here. Those make up basically the main body of the wall where we don't have windows. So that's the main structure of the wall. And again, we have the options of framing 16 and 24 inches on center usually. Here, I chose to go 24 inches on center. It makes for a little bit more energy efficiency. Some people term it as advanced framing or value engineered framing. I just call it, keep it simple, 24 inches on center framing. So, common stud. When you have a window opening, which this represents here, this all in the future will get cut out, the sheathing here. You have basically the rough sill, which you see here, which is basically the stud horizontally, so that frames the opening on the bottom. What supports the rough sill are called cripples. So the cripples are nothing more than common studs that got cut to support the sill at whatever that given dimension is. On the sides of the windows, you'll see we have our header and head plate, but we have two jacks here. And the jacks basically go up and they jack up the header. That's where they come from. Some guys call them trimmers. I've seen some books call them trimmers too. They trim out the opening. And then next to the jacks, you'll see we have our king stud. So the king stud is nothing more than a common stud. It's just the difference between a common stud and a king stud is the king is adjacent to the jacks, and it's the stud that goes all the way up and to the top plate and frames that rough opening for the window with the jacks inside it. So in this window here, you'll notice we have two jacks. So in our drawing, or in my drawings, I have it called out. Any window openings up to and including 3 feet, we would just have a single jack. Any opening that exceeds 3 feet has to move to double jacks, and if it's a very large opening, we'll have specific instructions there. But that directly comes from our structural engineer. So up to 3 feet, single jack. In excess of 3 feet, we do a double jack. So the double jack, like I said, it goes up to a header. In our drawings, we have a header schedule. So basically the header can change sometimes, and it doesn't necessarily change in dimension. I like to keep a very consistent dimension. Here we use 9.5 inch LVLs, but what changes is whether it's 1 3/4 inches or 3.5 or 5.25, meaning is it a single ply, a double ply, or a triple ply. You can see here most of our windows are framed as single ply, so they have just one header up there. And basically the top, you'll see we have a double top plate there. And the reason for 2 plates is that as you run these walls down the length, that top plate, the top plate of the double plate has the ability to lap the lower plates so that we get to build this wall not necessarily as one wall, but we get to tie that in for rigidity purposes. So we have that top plate. Then I take the header, the 9.5 inch header, and it's called to push directly underneath the top plate. And then we finish it off with what I call a head plate, which is nothing more than a twin to the rough sill that goes up there. And then the double jacks support that whole system. Now, there's a lot of ways to do it. You might have seen some guys, and I have done it in my past years, where we'll take the header, we'll put rigid insulation in between 2 2x10s or in between 2 LVLs. But as I've kind of gone through an experience and some iterations in thinking about it, now I just do what I call a header pocket. I push the header tight to the outside, I build it in plies towards the inside, but that you can see now leaves a 3 3.75 inch space or 3 1/4 inch space there to be insulated. And you know, we can leave it open, or in some cases we'll put 2x4s on the flat there, but so we can still put insulation behind it. So I don't have to necessarily insulate it at the framing stage. I can leave it as a framing pocket. The beauty of that is the framers do what the framers do when the framers do it, and the insulator does what the insulator does when it's time to insulate. So we're not asking somebody to do something out of sequence, out of order, or maybe above and beyond what they're used to. the framers are simply framing it. So we get that header pocket, but adding that 3 inches of insulation there gives me a little bit more energy efficiency. And as you can see, I mean, when you go fan down a wall, the headers make up a decent amount of framing above these windows and in the wall. So every little bit adds up when you're calculating that efficiency. Now, one of the other beauties of going to a singular depth in header, and in this case 9.5 inches, is when I push it up, it gives me basically a head height of 7'11" here in a 9-foot tall wall. And as you can see again, as we fan down here, because we're pushing all the 9.5 inch LVLs up tight to the underside of the double top plate and then pushing the head plate up to it, I get a nice uniformed look around the house. And if we went outside and looked at it, we would see that all of the headers or all of the tops of the windows are in nice perfect alignment. Now, why does that matter? Well, when you're putting siding up, we can course out the siding nice and neat, and we can really give that, hey, that looks very intentional, everything's laid out perfectly, and we can get that nice cohesive look in the framing and in the windows and in the aesthetics as we complete the job. Over here now, we have a much larger window. As you can see, I mean, this one here measures something like 9.5 feet by, I think it's almost about 10 feet or so in width. So yeah, stay tuned. When we install that, that should make for some good video. But here you can see we used the LVL studs. This is a wall. It's probably on the order of about 13 feet tall. And when you get into those kind of heights, and you can see here that we've probably taken about 80% of the wall and made it a window. So there's not a lot of rigidity. So we only have small spaces. So the key here is by moving to the LVL studs and getting that additional strength, we're able to stiffen that wall in the small areas that we do have it. Plus, we don't have any twisting, warping, any movement in those studs because they're engineered studs. They're a very, very stable material. So, but anyway, so you can see here, just because this is a larger opening than the one we just talked about, all of the rules still apply. We have cripples, we have a rough sill, we have our double jacks under the header, we have our pocket header here. Now, because of the size here, you can see that that pocket is a little shallower, and it's because that's a 2-ply beam up there. So we have a 3.5 inch by 9.5 inch header that goes out to the double jacks. And yeah, just because it's a larger opening, we change a little bit of the rules, but pretty much the framing stays the same. It's really important that we maintain some level of consistency so that we're not asking the framer do this over here and then switch to this system and then switch to that system. You know, everything's the same dimension. Here we're just asking, hey, switch from the standard studs and move into the LVL studs. So all of these things kind of come into play when I'm sitting at my desk and we're talking in the office and thinking about how are we going to put this together. All of these are rolling through my heads, how we're making the header, in my conversations with the structural engineer, in my conversations with the homeowner, to make sure that we're all on the same page. So by the time it gets here, we've already made hundreds of decisions to get us to this point, and now we're just working with the framer to make it all complete. So let's go over and we'll catch up with the framer and we'll talk about putting a wall together. All right. Hey, Matt.
Hey.
How you doing, buddy?
Good, how you doing?
So,
good to see you.
everybody, Matt King. Matt King's in charge of Matt King Construction. He's the framing contractor out here. So, Matt, we've just been talking a lot about the framing. I figured we'd catch up with you and maybe talk a little bit about your process here. So, if you want to, just give us the lowdown of, you got the floor framing down. Where do you go from there?
Yeah, so, we start by squaring up the rim board, and we get all of our lines snapped around the perimeter. And then you know, we start with through walls. We do, you know, try to do one side, you know, one side of the house, opposite sides. That way, when we have them down, you can build them at the same time, and then you stand them, and then you build the ones on the inside.
And by through walls, you mean walls that go all the way to the end of the floor,
correct. Yep.
right? Are you the guy doing the layout here?
So it's either
part?
myself or there's probably 2 or 3 other guys that can read the plans and are trusted
And
enough
interpret it. So there's a little bit of logistics, a little bit of puzzle, there's a little bit of wisdom and experience in pulling from this side, laying it out. And so you're looking at guys that have done this quite often. And then so you do the layout. I've seen framers, you know, work obviously, but you always lay out 2 plates at the same time. So you basically do them in twins so that the bottom plate and the top plate acknowledge the same markings.
Right.
And then you get into laying out, and we talked earlier about, you know, I talked about the components of the wall framing, the jacks and trimmers. So you have your system where you put J and K and cripples, and so guys then can take this, once you have the rough opening established, then you have the heights of the jacks, the heights of the cripples, and all of this stuff where you just have guys just sitting there cutting all these pieces.
Right. So typically we'll try and write the dimensions of the components for the window. Like the guy laying out will write it on the plate. That way, if he's over there with the plan, the guy building the wall can say, okay, my jacks are this is the header that I'm going to use, this is the rough opening of the window, and from there they can usually take it. And
so there's a lot of like teamwork, you could say, that someone's figuring it out, but they're dropping that information for other people to come by, grab onto that information. So because the one thing that I've always acknowledged about framing crews and that I'm always impressed with is you go out to a framing job, you never see somebody standing around.
No.
That's like a rule breaker, right?
Yeah, we asses and elbows, we say.
Yeah, so there's always something to do on a framing job.
Right.
If at the very least, clean up the mess, roll up an extension cord, do something.
Right.
But there's always something to do.
Absolutely.
So the materials that we're using here, obviously I've done a number of projects with you, so you're not, you know, there's nothing of a mystery here to you. We're using the zip R sheathing. I'm assuming you're starting to see that a lot more.
Yeah, especially in commercial. Usually commercial, they spec it out, but some houses are lucky enough to get it as well. So this happens to be one of them.
Got you. So that probably takes in a little different coordination effort as far as managing the corners, managing length of walls, because you've added that 2-inch thickness to the wall. So there's just slightly different math that you're applying to, right?
Right.
So, all right. Well, I don't want to stop you, man.
Yeah.
Thanks for taking the time to have a chat with us. Everything looks great, buddy. Thank you.
Sounds good. No problem.
All right. So we're over in one corner of the house. One of the last things I want to talk about is the building science of a wall assembly. Now, we talked about earlier about things being climate tuned to certain climate zones. And as I stated, we're in climate zone 5 here, which is considered a cold climate or a heating dominated climate, right? Yeah, we have nice warm summers, but we're predominantly a cold climate where we do more heating than we do cooling, as opposed to say like Arizona, Phoenix, or Miami, Florida, which is a cooling dominated climate. So in a heating dominated climate, when I look at wall assemblies, I like to think of the 3 parts of a wall assembly. And the 3 parts are, sometimes they're not components, they're the absence of components. So the first part is the cavity. The cavity makes up what happens in between the studs. The second part is what I call the opaque part of the wall, or opaque framing, which is basically just all of the areas that the framing members make up. And then lastly is the window opening. Here we have a corner window unit. This one just isn't cut out just yet, but we have that one. Then we have this large one here that makes up the corner. But those are basically the 3 components of a wall assembly. And let's say 3.5 components, because the other part is what happens on the outside of the wall. And in the case here, we have the zip system R sheathing, Zip R9 board. You can see it's got that laminated 2 inches or 1.5 inches of polyisocyanate right there that gives us an additional R9. So if I think about the wall, if I take all of these exterior walls and I put them all together and create one wall assembly that is all three of these components, and then I look at those components individually, I would come to understand that the cavity probably makes up something like 60 to 65% of the wall system. The opaque nature of the wall, or all of the framing cumulatively, probably makes up somewhere in a, let's say 16 to 18%, 20% of that wall system. And then in the case here, the windows probably make up an additional 20% of the wall. So I have those three components. Each one of those three components have an R value, or when you're dealing with measuring the resistance, you actually deal with the U value, which is the reciprocal of the R value. But in the case here, we'll talk into more common knowledge of R value. So the cavity, 5.5 inches, we're probably looking at putting in an insulation. Typically you'd put in something in an R21 to R25 range, depending on what you put in there. Now remember, that's 60% of the wall. The stud, 2x6 stud, that carries about 5.8. Let's just call it R6 for easy math. And then the windows here, we're using a high performance window. We're going to be up in the R6, R7 range with our windows in the triple glazing. So you can see here that basically the window and the framing carry roughly the same R value, but those two pieces, which make up roughly, just under 40% of the wall, those are carrying about a third of what the cavity covers. So by going to the 24-inch, for example, that takes our opaque framing number. It takes it from that standard of the 16, 18%. It moves it down and maybe to a 12, 14% range. So that shift in, say, 5-6 percentage points, well, that goes to the cavity. So that's how we get that kind of bump up, that energy efficiency, in that the R value in the cavity now just got bumped by virtue of going to the 24-inch on center. It got bumped that additional 6%. But if I take those three numbers and I normalize them across all of the walls in the house based on their respective areas, then I would come to find out that what I would term the whole wall R value is significantly less than, say, that R23 or R21 that we would typically call our wall framing. It's probably close to about half of that, right? And we're going to talk about these numbers when I go back to the studio in more detail. But the one thing that I wanted to chat with you about here in closing is the one huge benefit to dealing with energy efficiency in a cold climate is exactly what we do to ourselves. We put a jacket on, right? And that jacket wraps us up. It keeps us nice and warm in the winter. So why wouldn't we do that to our houses, right? And hence, that's where the Zip R9 comes into play. So if I take that same math that I was just talking about, and I have that R6 here, well, the minute I put R9 on the outside, now I have R15 at the opaque area. Where I had the cavity of, say, R21 and I had the R9, now I have R30 at that area. So you can see in that 80% of the wall frame, I've significantly enhanced the R value by using the continuous insulation on the outside. So when we get back to the studio, I'm going to break out some serious numbers. We'll go through the math and we'll talk about it more there. But that'll give you a general sense of, when you're thinking about the efficiency of a wall system, what should I be thinking about? Hey, look it, we caught Matt here, and we got some taping going on. Hey, Matt.
Hey.
I caught you perfect time in here.
Yep.
So we got the wall framed, we got the sheathing on here. Now, we're very fortunate on this job here that Huber Engineered Woods chose to partner with us, so they provided all of the Zip R9 for the project, which is a really good deal for Scott and Jonathan here. But I can see that we're completing the system here. So let's talk a little bit about the tape. Standard 3.5-inch flashing tape. It's a cold weather tape, so it can be applied in colder temperatures. I don't exactly know which one it is, but it goes down pretty darn low. And is there any method to your madness here?
It's really pretty simple. I mean, the first thing you want to do though is just make sure that the tape always overlaps as you go up. So you always start on the bottom and go
Work
up.
your way to the top. So if there's any water flowing down through our rain screen system, it's always operating over a shingle fashion tape install, right?
So you just think like a water droplet.
Think like a water droplet. There you have it, folks. So you apply the tape. Is there anything that we have to do to the tape? I mean, I know some of the answers to these questions, but
yeah. So I mean, you just try and keep it as straight as possible. In this situation, we don't have any overlap, so we can just kind of go ahead and get it going. But you know, you just get a few on, get the roller, roll it out real good, and make sure it's on there nice.
And the cool thing about that roller is you can see here that it has the Z's embossed in the tape, so that as you roll it, as far as quality control, you don't have to, you know, go and tug at it or do anything. Just a real quick visual inspection, you know that somebody rolled it.
Yep.
And then we get a nice adhered tape. So, I mean, it's interesting. The very first time I used zip was probably around 2009, 2010. I took two pieces, taped them together, and they're out on my wood pile at my house because I just wanted to see how it lasts.
Right.
It's like it was taped yesterday.
Yeah.
It's an incredible system. I know a lot of people are leery of using tapes and adhesives in their project, but Zip's got this system down.
Zip, I mean, the tape itself is a great product. It's,
yeah, I mean, I would suspect that after you roll it, if we tried to tear that up tomorrow, we'd probably take, you know, the facing off of the OSB before the tape is going to come off.
You can't get it up. Once it's on there and it's got a little bit of the heat on it, it's not coming up for anything.
All right. Well, again, thank you very much.
Yep.
It was great catching up with you, talking about the Zip system here, and let's get some more walls up.
Sounds good.
That Bill Joe. I'm not here just to talk. I'm working today. So you can see Matt's putting on one of the metal braces, so it actually acts as kind of a temporary brace at the moment, holding the wall in place. But the beauty of these braces are, you can see down at the bottom here, they're going to attach it to a 2x that they nail in. But notice at the bottom of the brace that it actually has a screw jack component to it. So they'll put the screws in there now. It'll temporarily hold the wall in place. But the beauty of that is, after they're done with all of the walls, they'll come in, they'll run a bunch of string lines, they'll double check everything, but by simply rotating those braces, they can push this wall in or out and get everything perfectly square and tight and plumb all in one exercise and get it all set up so we'll be ready for the roof frame. All right, Jared and Matt. So, wall framing. Things are well in hand here. Things are looking really good. We've got a few more walls. We still have that one big monster. That's going to be a treat to see that one go up. But I think that's a wrap for today at least.
That's it. Working our way through it. Before you know it, we'll have roof on, walls will be complete. This thing's moving, going along nicely.
It's moving along nicely. And it'll be sad. I get so excited when framing is here and then it's gone. So, anyways, buddy, I'll catch up with you.
All right, man.
And you have a great day.
Thank you.
All righty, we're back at the studio. Big Red in hand. We got some drawings. Hopefully you really enjoyed it. Wall framing. Wall framing's three-dimensional. You put the floor framing in. Yeah, it's nice, but you walk across it. Wall framing, you got walls. You're starting to see stuff. It's exciting times. So I have a couple drawings here. This is going to be a little twist on wall framing. We'll do a little introduction about what we're going to do there, but I'm going to take up a little bit of controversy, and we're going to talk about why I think the industry is lying to us all just a little bit. Maybe I shouldn't use lying, but maybe misleading. So I'm going to give you some inside info, strictly building science, and we're going to talk about walls and wall framing and everything that's happening from a building science perspective to that wall system as far as energy efficiency goes. So let's talk about the wall section first. So let's talk about the wall section here. Get out Big Red. Give you a quick orientation. Last time in the floor framing, we talked about the foundation. We have our double mud sill. We have our band joist here. We have our bottom plate there. We're using a 2x6, and we're doing it 24 inches on center there. And so that gives us basically 5.5 inches to work with from a cavity perspective. But we're also using zip R9 on the outside of the wall. And the zip R9 is basically 1.5 inches of polyiso. For those not familiar, it's polyisocyanurate. Rigid insulation. And that is laminated to a 7/16 OSB, which is their standard zip. So together, those make 1.15 inches insulating sheathing on the outside of the wall. Inside that 2x6, 5.5 inch cavity, we will be insulating with 2 inches of natural polymers. And natural polymers is a closed cell spray foam. So some people call this a flash. And then we are going to do a blown in insulation in the remaining 3.5 inch cavity there. But let's get into the wall height that we're using here is 9 foot 1 inch. And all of our head heights, when we were out there, we talked a little bit about that. But our head heights come in at 7 or 8 foot. So no, it is 7 foot 11, sorry. Too many numbers. And the way we do that is we have our double top plate on the top, and then we basically have a 9.5 inch header height. And I say header height because we have a header schedule. So sometimes that is a 1 ply, sometimes it's a 2 ply, and actually sometimes it's a 3 ply, because we can fill that right up. In most cases, the windows, it's a single ply, and so it only comes in the 1 3/4. So that leaves us some remaining cavity that we will spray the natural polymers in. I like to call that detail a pocket header. And you saw it when we were walking around out there. But the pocket header basically enhances the thermal control layer where all the headers are. You know, traditionally you would do this built up header where they would do 3 2x10s or 3 2x12s with 1/2 inch plywood, and you'd be at roughly, you know, I don't know, R7-ish, right? By doing the pocket header, we are 7. We're probably somewhere around R28-ish would be my guess. So far better situation to be using that pocket header. And then of course our roof framing happens above that, and we'll be talking about that here in the next episode. So that's our basic layout on the wall framing. But what I wanted to get into is the R value when we talk about our wall systems, and this is where the industry is a little misleading. If I sat here and said, okay, we have 3.5 inches of blown at, let's just use 4 inches for an easy number. That's 12, 14, 15. So that's roughly about R15 for the blown in. We have 2 inches of natural polymers at 13, and then we have 9 on the outside. So we're talking roughly R37, is that? Yeah, R37, R36. I used R36 there, so we'll just run with that. Let's say the 15 is, we'll just call that 14. Or no, it is 15. Yeah, or 14. So let's just say it's R36. So I could very easily go around and boast, hey, we're building this exceptional wall system. It's an R36 wall system. But I would be misleading you. So I'm not going to do that. The R36 is the center of cavity R value, right? So we'll call it COC, center of cavity. But what we don't usually talk about in a wall system is what happens where the windows are, what happens where the doors are, what happens where all of the framing members are, right? So that R36 is all good and well at the center of cavity, but where we have a framing member and that stud is, say, R7 across there for 5.5 inches. I use roughly about 1.25 inches. R value, it depends on wood species and all of that stuff, yes. But R7, and then we have the R9 on the outside, that's R16. R16, and what I call it there is, we'll call that the OF, or opaque framing, right? So you can see we go from 36 down to 16. That's a pretty significant drop. The question is, what are the percentages that we're looking at here in the wall framing? But clearly, we're not building an R36 wall if a good percentage of the wall is only R16. That number is going to come down. So let's add in the third component. We have a series of windows and doors here. If we did a standard domestic product and met code, we would be at something like R3. We're using an enhanced European tilt turn window system here. So we're going to bump that up to roughly around R7. But the R7 from the 36 is about 20% of our stated R value. So if I go around and I say, hey, I'm building an R36 wall, well, no, you're not. I'm building an R36 wall for a large percentage of the wall. A certain percentage of the wall, I'm only building R16. And all those little holes that I cut in the wall, and in this case, we have some very large holes because we have some very large windows that Schuco USA is building us some beauty. So I can't wait to shoot that video and go to the factory and see these things get built. But where we have those very large windows, at best, we're at R7. So we're not nearly anywhere near the R36. So I took a wall out of the house and I did a wall framing elevation. I threw some percentages against it. I threw some numbers against it. Now, some of you might use slightly different numbers. That's okay. This is historical data. I actually went back and looked. For years at Building Science Corporation, I worked with framing crews and getting them to move to 24 inches on center, actually going out to houses, counting studs, doing wall framing elevations for whole houses, and then doing them 24 inch on center, 16 inch on center, comparing those numbers, getting those percentages and getting a very clear understanding. So my numbers might be slightly different than yours, but my numbers aren't lying. These are very valid historical precedents. So let's just take a look at them. The first wall that we're going to talk about, it's a 2x6 wall, standard framed, 2x6, 16-inch on center. This one just has regular zip, and or it could be plywood sheathing, but it has no insulating sheathing attached to it. It is just the structural sheathing. If I look at this, my opaque frame accounts for 20% of the wall at R7. Okay, so 1/5 of the wall is at R7. The cavity is roughly 60%, and that's at R21. That's basically a code number. And then the doors and windows account for roughly 20% of the overall walls. Now, understand, these percentages are taking all of the walls of this house, cumulatively adding them up, and then basically saying, hey, if we did a chart where we graphed all of the walls, well, 20% of it here would be opaque framing, 20% of it would be doors and windows, and 60% of it would be cavity. So it would be distributed along those lines. And understand that in this case, this is 7, this is 3, and this is 21. Well, guess what happens when I take those percentages, and we'll write them up on top here, 20, 20, and 60. When I take those percentages and these R values, and then I average them respective of their percentages in the wall system, I get what's called a whole wall R value of R8. So builders, insulators, everybody, if you talk to them and said, hey, what kind of wall are you building? Oh, we're building an R21 wall. Yeah, you are. Center of cavity for 60% of the wall. If you really want to talk about what you're doing, you're building an R8 wall assembly. And the wall assembly is the whole wall R value, right? That's taking all the components of the wall systems, all of their R values, and averaging them to get that number. Now, here's a little glitch, because I know some of you out there are going to take these numbers, you're going to go do the math, and you're going to come back and say, hey, Steve, my numbers don't match up to yours, because I've written articles on this, I've done other videos, and I get those comments all the time. Understand that when you do these, you have to switch all these R values to U values, do the calculations, get the answer in U value, and then invert it to the R value to come up with the R8. You can't do the math as R values, especially when we get into insulating sheathing, because the temperature and the work of the insulation changes as you migrate through the insulations, right? If I have a wall that has insulating sheathing versus a wall that doesn't have insulating sheathing, the outside of the cavity insulation is far colder without the insulating sheathing. So you can't do it by R value, you have to do it by U value. So let's press on. I have another wall here. This is simply moving the studs out from the 16-inch on center to a 24-inch on center frame, staying with the 2x6, staying with the standard board sheathing, either zip, plywood, whatever structural panel you want to use, but it's a non-insulating panel. So let's see how the numbers differ. If I move to this, and some people would call this advanced framing. I've heard people call it OVE, optimum value engineered framing. There's a lot of names. Me, I call it 2x6 24-inch on center framing, because that's what we're doing. So if we look at these numbers, the opaque frame, We go down to 14% from the 20%. So we gain 6%. Where does that 6% go? Yes, it gets added to the 60% of the cavity there and basically moves that up to 66. R21, we keep the window and doors. So if I do my overall whole wall graph and I say 20% here, well, that would be for the doors and windows, right? And then the opaque frame would just go down to 14%, and this would be 66% for the cavity. I know I've been writing it up there. All right, and that's 21, this is 7, and that is 3. But if we look at those numbers, you'll see that, yeah, it goes up, but it went from R8 simply to R9. So you might hear a lot of people say, oh my God, I do advanced framing because it enhances the insulation package. It does. They're not lying. But it isn't the end-all, save-all to a good house being built. Because you can see here, it moved the R value basically 1 point from 8 to 9 by going to the 24 inches on center. It didn't double the number. It increased it by what? Maybe 10 or about 12%, right? So it's not a whole lot, but it is an improvement. So I'm not saying don't do it. What I'm saying is don't sit there and believe that because I'm doing advanced framing or OVE framing that I'm rewriting the book on energy efficiency, because you're not. All right. Now let's take a look at what we're doing out here at Build Show Build Boston, and you'll understand why we made some of the decisions that we made out there. If we look at it, we're doing 2x6 24-inch on center, but we're adding an R9 insulating panel. You can see it on the outside there. So what does that do? And I'm just going to put this math across here. It elevates our framing to R16. Our number there was R7. Our number there was R7. We're almost double here. Why are we double? Because everywhere we have a stud, we have zip R9 on the outside. So we effectively doubled the insulating R value of our opaque frame. And by going to the 24-inch on center, we took our 20%, dropped it to 14. So I've optimized both sides of that number, right? I have 14% of the wall system at R16 now, not R7. Moving on to the cavity, 66%, that's that 66%, that 6% shift here because we went to the 24-inch on center. And you can see here, because we have that cavity R value, in this case here, what did I say? We're at 36. That R9 also gets added to the cavity insulation, right? And we had the cavity insulation at roughly R27. So it's that R27 plus the R9, and that gets us to the R36, right? R36 is significantly higher than the 21 there. And we've optimized both the percentage and the R value once again. So in both of those, they've increased. Door and window, the 20% doesn't change because unless we take windows out and add walls, that number isn't going to change. But we moved to a triple glazed European style tilt, turn, and fixed window assembly, meaning that some of them are tilt turn, some of them are tilt only. We have a lift and slide door, and a bunch of the windows are fixed. And these are all being made by Schuco USA. So they're a fine aluminum frame, thermally broken, triple glazed window, but they are coming in at roughly R7 for the same 20%. But when I look up here at the standard code dictated, mostly widely used domestic product, we're at R3. So I've more than doubled that number. So you can see in all three instances, I've made a significant impact. And you can see here, the whole wall R value here is that number times 2. And we're getting an R18 wall system. Now, I'd like to sit there and say, wow, we're doing something great, which we are. But understand, up here at this code-built wall, right, and builders saying, oh yeah, this house here has R21. We're building R21 walls. You're not. You're building the R8 walls. After moving to 24 inches on center, adding zip R9 and upgrading the windows, we still haven't accomplished their misleading. We're getting closer, but we haven't accomplished their misleading. We would have to do some other things. We could go to a thicker insulating sheathing. I have some houses where we do a 2x8 wall with staggered stud framing, or if you want the kind of Ferrari of walls, we can move to a 12-inch double wall system and really enhance those numbers. But understand, this is kind of the spectrum of capabilities of a 2x6 wall. But you can see that just by making some choices, moving to a product like the Zip R9, moving to a triple glazed window, by Schuco USA, that we're moving in the right direction here, as well as, putting the closed cell and not basically just blowing it in, doing that flash and bat. For that first 2 inches, we're at R13, not R8. So there's an enhanced value there of getting us up to that 36. But look at this number. This is pretty interesting. Look at this relationship, right? If I walked around and said, hey, we're building an R36 wall. No, we're not. We're building 50% of that number. And we're building an R18 wall. So there you have it. That's the building science of wall assemblies. Those are the decisions that you should be talking about with your clients, or if you are the client, these are the decisions you should be talking about with your builder, with your architect and or designer, and try and get an understanding of what matrix is the one that works for you. Before we go, I just want to make one last point. A lot of people associate energy efficiency with cold climates. Hey, Minneapolis, it's cold, got to put insulating sheathing on there, right? Do I have the same considerations in a house that I'm building in Texas? So I say yes. I'm building some houses in Texas right now. Triple glazed windows. We got Zip R6. We didn't have to move to the R9, but we certainly did the R6 because that's enhancing the wall system. Let me just give you the quick Steve Basic 101 on energy. It's a two-headed monster. We want to convert energy as inexpensively as possible, and then we want to hold on to it as long as possible, right? So energy, it only moves from, ready for this? Hot to cold. What's interesting is I hear a lot of people say, oh, I'm trying to keep the cold out, so I'm going to insulate my house. Or, people will say, in Texas or Florida, oh, I'm trying to keep the cold in down here. No, you're not. You're never battling cold, ever. Cold doesn't move. Heat moves. And it moves from hot to cold. So in a northern climate, like we are here, climate zone 5, and you can go online, just Google climate zone map. You'll see the I think it's 7 zones across the United States. You can see where you fall into that. And in the heating climates, yeah, it's real easy to sit there and say hot to cold because we're providing heat on the inside and it's trying to go outside of my wall system. So yeah, I put up insulation. It's like putting a jacket on when I go out in February in Boston, right? I want to stay warm. I put insulation on. It keeps the heat generated in my body from being released to the outside and warming up everything that's cold around me. So it insulates me. Now in Texas, when it's, I'm gonna find some clean space here. Let's just say it's 90 degrees outside and I'm trying to keep it just simply 70 degrees inside. Well, I have a 20-degree delta. Guess what? Heat is still trying to get across that wall. And the only way to stop heat from moving across the wall is to provide resistance. And what is resistance? R value, right? That's where that little R comes in. It's the thermal resistance value, the R value. So when it's 90 outside and 70 inside, that heat is trying to migrate in. How do I battle it? By putting a series of insulation across that wall to slow that heat transfer, because heat moves from hot to cold. Stop saying the cold moves. It doesn't. It's hot to cold. And that's wall framing. Next up, roof framing. That's where we cap it off. See what I did there?